All right, we're gonna do more derivatives today. Yay. Okay, so we are trying to find all of the derivatives of psi that are in equation exclamation point. So we've already done the derivative with respect to x and y. We also need an xy, a yy, and a yyy.
Why indeed?
Y indeed. Okay, so let's do, I'm gonna put it here. Where am I gonna put it? Let's put it here because it kind of depends on this one. So next we're gonna do psi xy. So we have partial y of the result from before. So u infinity dl dx times the quantity f of eta minus df d eta times eta. And I just had space to close that grouping. I think I have them all in there. Alrighty. What's up, man?
Huh?
Oh yeah, Jalen's here.
I know, I'm here for once.
Are you coming to the thing tonight? Good man. Okay. All right. Shame to your family.
She did come to my house and knock on my door, so
I talked to his parents. I was like, he's gotta be here. Okay.
Dr. Beatham shows violence today.
I'll try to.
Okay. U infinity is a constant, so I'm gonna take it out front. And partial L partial X is also a constant relative to Y. So I will put those out front. Is this a terrible place for me to be doing this? Do you want me to move it down a line?
I don't really care.
Is anyone offended by this?
Honestly, that's how I do it. And every time I do it, I feel like I hope I'm not offending the person rating this.
You have regrets?
No, I don't
feel
regret
like
it.
it looks good because you have the little arrow separating it from the other ones.
That's
I feel like
true.
it's
Okay, that's true. Okay. Okay, so in the bracket, I'm gonna need to do the chain rule because eta depends on y. So I will have in here df d eta dy minus second derivative with respect to f, or sorry, with respect to eta of f, and then d eta dy times this eta, and then I need to do the product rule here. So I have df, d eta, and then d eta dy. And this has an equal sign. I'm not going to do that. I don't like when I don't see equal signs. Anyway, never do that. Okay. All right. Remember df d eta, or sorry, d eta dy is 1 over L of x. So this is 1 over L of x, right? Here and here and here. So we have u infinity dl dx is df d eta times 1 over L of x minus second derivative of f with respect to eta over L of x minus first derivative with respect to eta of f times 1 over L of x. Let's make sure I arrived at the same answer. F over L. Yes. Good. Okay. Notice that we have two terms that are the same, but with opposite signs. So these two terms cancel one another.
love to see.
You do love to see it. It's like, love it when a plan comes together. All right. So we have minus u infinity dl dx, second derivative of f with respect to eta times eta over L. Okay, and note psi xy is equal to psi yx because we're assuming that the stream function is smooth and continuously differentiable. Okay, so let me just put a little divider in here. So we have that. Lovely. Now we need to take some more subsequent derivatives with respect to y. So we need psi y and then psi y. That was 3, right? Y. Yes. Okay. So let's do psi y first. All right, so I'm going to take the y derivative of our result that we have on the previous line. So we have u infinity df d eta. Again, I'm going to do the chain rule because eta depends on y. So I have u infinity, second derivative of f with respect to eta times d eta dy, which is u infinity, and then I pick up a factor of 1 over L. Okay, and then when I do another derivative with respect to y, I am going to get a similar thing. So I'm going to increment up the derivative of f with respect to eta, and then I pick up another factor of 1 over L. But I will write it out for posterity. Okay, so we have u infinity over L of x, second derivative of f with respect to eta. And then that is, I have u infinity over L of x out front because it's constant with respect to y. Then I have the third derivative of f with respect to eta times d eta dy, which gives us that extra factor of L over x, or L of x, sorry. So this is squared. And then we have our third derivative with respect to eta. Okay, so substituting all of this into our equation exclamation point gives us hang on, let me just, I'm gonna just copy this for my own convenience. Okay, so I have psi y is u infinity df d eta times psi xy, which is minus u infinity dl dx, second derivative of f with respect to eta, times eta over L, minus psi x, which is u infinity dl dx times the quantity f minus df d eta times eta, and that is equal to nu times psi yy, which is u infinity over L of x squared, third derivative of f with respect to eta. And now I can get rid of that. Okay. So I have a u infinity out front of all of these terms. So I'm going to divide through by u infinity so I can get rid of this one, and this one. Let's see. I also, let me just write this out. Sorry, I think there's a cancellation, but let me just write this out. So I have minus u infinity dl dx eta over L. And then I have df d eta times the second derivative of f with respect to eta minus dl dx f plus dl dx df d eta times eta.
Why did that other unit not cancel?
What?
Why did that
It's
other
not-
unit not cancel?
Because it's multiplied. Right?
I see.
Yeah, that one's got to stay.
Sorry, I haven't
No, it's
been
okay.
typing.
This is interesting. Okay, and then this we have new over L squared, and then the third derivative of f with respect to eta. What's interesting is it seems, at least based on the notes that I'm working from, is that, stop. Where is it? This guy. This term does not exist for reasons unknown to me at the moment. I expanded this correctly, right?
We forget to multiply by psi yy.
Oh, did I forget something? Did I forget a factor?
I think.
Oh, I
it's
think it's just psi x, isn't it?
Yeah.
Okay, all right, let's begin. I'm sorry, we're gonna have to back up. No, copy. Oh, I still have it. Okay, hang on. Okay, so sorry about this. So this term I need to. I'm sorry. So I'm gonna move this down here and then, okay, yes, because this is psi x. And then I need times psi yy. Okay. Which is u infinity times the second derivative of f with respect to eta d eta dy. And then I can move this guy back. What's that?
Are we gonna just change the d eta over dy to 1 over L?
Oh. Wait.
It's in the upper
Oh,
parts.
wait, I didn't. Yeah. I didn't. Okay. Copied the wrong line. Thank you. Over L of x. There. Is that good now?
I think so.
Okay, thank you. Okay. Okay, fantastic. So now I'm going to rewrite what we have left. So I have minus u infinity eta over L dl dx. And then I have a second derivative of f with respect to eta times a first derivative with respect to eta minus u infinity times dl dx, and then I have a 1 over L second derivative of f with respect to eta times f, and then plus u infinity over L times the second derivative of f with respect to eta times dl dx times df d eta times eta. Okay, and we notice I could have written it a little nicer, but we noticed that this term and this term are the same, but with opposite signs, right? I believe. Yes, okay, great. So we can cancel those. And then let's not forget the right-hand side. So we have new, just the one time, over L squared times the third degree derivative of F with respect to eta. All right. So I am gonna move everything over to one side of the equation. So I have, and then I'm also gonna divide by, I'm gonna divide through by this so that my leading order derivative has a coefficient of 1. Okay. Okay. So divide through by this. Okay. Great. So I have third derivative of f with respect to eta plus u infinity over L dl dx, and then I'm multiplying by L squared over nu second derivative of f with respect to eta times f, and that's equal to 0. So this simplifies to the third derivative of f with respect to eta plus u infinity times L over nu dl dx, second derivative of f with respect to eta times f, which is equal to 0. So not too bad, but this is still a very nonlinear third order differential equation. I said nonlinear, right? Yeah, okay. So here's our governing equation. What should we call this equation? Oh, I remember what Lee requested last time. No, that's a bad circle. Okay, there we go. Very cool. Okay. So now we're gonna solve that guy. Once I pull up my next set of notes. One moment, please hold.
First of all, music.
Huh?
Need some old music.
The whiteboard in here now.
I know.
Yeah, this is weird. And it says, please DND, do not disturb. Well, someone's sleeping next to it. I don't know. There's lots of questions I have about that.
Yes,
Huh?
never almost with the whiteboard.
I mean, these chairs were like facing each other and I'm like, what if someone was sleeping?
Genuinely got banged.
That would be the most uncomfortable configuration to sleep though.
Here
Two
I-
wheeled chairs. You assume it's a faculty member.
Yeah, well, isn't this a lot most of the time?
Yes. That's true. That is true.
Oh, what's the thing? It's always been mentioned.
I don't know. I never see it.
I don't know.
Okay, let's see. I want this guy.
We need to get like the Samsung video wall.
What's that?
The whole wall would just be a TV.
That would make me dizzy probably. I don't know. I'm not sure I can handle it. Like, you don't want me to play Max.
It's
Very overwhelming.
like $300,000 or something.
Yikes. All right. Where?
Where are we getting that?
What was this?
Big job.
The government.
I think the government's trying to give us less money, not more.
Yeah, wait, so I see my super cool video wall presentation.
I think you can some.
Oh, Aura.
I've been to her house. It's really funny.
The president?
Yeah,
Really?
yeah, I got to go inside her house.
Why?
For my Kings and Things class.
Kings and things?
Yeah, it's an honors college elective.
Oh, I assumed.
And
When it rhymes, when the class name rhymes.
class in Meadowbrook, in the Meadowbrook Library.
Hmm.
Like every class was in the Meadowbrook Library, and he was just like, and we got to go through all the secret staircases.
Oh.
And we got to go through a secret door in the men's restroom that leads to the organ pipes and the secret basketball court. And
Interesting.
we got into the president's house. We got to go into the president's house because, you know, part of Meadowbrook. So was Matilda's house after she was like, Meadowbrook Hall's too big. Let me have a smaller house with just like a couple servants and not like 20.
I mean, these are very common problems that people have.
Yes. indeed.
Yes.
So we got to go look
I
in there.
feel that on a spiritual level.
They're cool.
Okay. So what we're going to do first is the following. So remember, we're looking for a self-similar solution. Remember. Right, so by that, I mean that the shape of my velocity profile is going to be the same everywhere along the length of my plate scaled by something, right? So that's why we introduced eta and f. All right, so that is the assignment that we've set out to find. So that means that the solution for f is going to be independent of x. So it'll be a function of only eta. Which we've already kind of baked into this equation, to be honest, but f is not a function of x, and f is only a function of eta. All right, so by nature of this construction, that's why I have all those total derivatives in there anyways. But I'm just reminding you. Secondly, since that factor out front of our second term, so u infinity times L over nu times dl dx is not a function of y. And it's also not a function of eta. Then it must be a constant. Oh, thank you.
You wound that up too.
I always do. I'm sorry.
I'm sorry, man, that's messed up.
It's dramatic. I can't not. It's part of my personality.
I didn't even call you out, my bad.
It's fine. That's why I only got to do the one instead of the three I needed. Okay. So that means that we can do the following. So we can, why would I do that? Sorry.
You might be telling us what you're thinking.
You're very expressive about your emotions about your notes.
Sorry. Okay.
Good.
So we're gonna write this as, I don't really like how this is. So I'm gonna try something different. Sorry. I'm gonna call this. equal to C1, some constant, because we know it's a constant, right? And then I'm going to separate variables and I'm going to integrate it. All right, so I've got L's and DL's on the left, and then I'm going to put DX on the right. So I have U infinity times L over nu times DL is equal to C1 dx. And then I'm going to integrate this guy. So that means we have U infinity over 2 nu L squared is equal to C1x plus a constant. And we know that, oops. L has to be equal to 0 when x is equal to 0, which means that C2 is 0. Okay. Oh, I like my way much better. Not to brag. Okay, so we have that U infinity times L squared over 2 times nu, and then I'm going to move my constant over here is equal to x. Actually, no, sorry. I'm going to keep it over on the other side. So C1x. And then I'm going to solve this for L of x. So this means that L of x is equal to the square root of 2C1 times x times nu over U infinity. And then I'm going to note that I can rewrite this as the square root of 2C1 times the square root of x times nu over U infinity, where this factor out front is just some constant that will depend on whatever C1 is, right? So it's just some arbitrary constant, which means that our function L of x is proportional to, I'm going to call this constant b because it doesn't matter now. So we have b times the square root, times the square root of x times nu over U infinity. Which hang on, let's remember that we have, where's my definition for delta? It's way up here, isn't it? So observe, actually, I'll copy this. So we know that delta scales like square root of nu L over U infinity, which is a very similar form to what we just found, right? So let me I'll rewrite it. So remember, so delta scales with the square root of viscosity times some length scale over U infinity, which means that L scales with delta times some scaling factor B. Cool, right? Yeah. Okay, so what does this mean? This means that our boundary layer thickness grows as square root of x square root of nu and 1 over the square root of u infinity. Okay. Okay. Do not love that. All right. So okay. Now looking back at equation sunglass face. We can let C1 be 1/2. So essentially we are letting u infinity times L over nu dl dx equal to 1/2. U infinity times L over nu dl dx is equal to 1/2. So our equation is then just the following. So we have f triple prime plus 1/2 f times f double prime is equal to 0. So note f prime is df d eta. F only depends on eta, so I'm going to switch to primes now. Okay, so this is a nonlinear ODE. Third, this is not how you spell linear. That's how you spell liner. They put a dash here. Ugh. There. Okay. And it has the following boundary conditions, which I believe we've written down before already. So we know that u of y equals 0 is equal to 0. And we know that u at y goes to infinity is equal to u infinity. And we also have that v at y equals 0 is equal to 0. So we have no slip, no penetration condition, and then very far away from the plate, the free stream velocity is returned, right? Okay, so let's translate those boundary conditions into F's and eta conditions. So what's wrong?
Nothing.
Oh,
I was
okay.
just reading stickers on your laptop.
Oh, okay, that's fair. That's fine. I'll allow it. So we have F at eta equals 0 is equal to 0. Oh, I'm sorry. This is F prime at eta equals 0 is equal to 0. This one is F prime at eta goes to infinity is equal to 1. And this is F of 0 is equal to 0. Okay. And the solution to this, so let me put a box around this. So this is the equation that we want to solve. And the solution to this is called the Blassius solution. as you may have suspected. All right. Okay. And given this setup, we know that u of x and y normalized by u infinity is equal to f prime of eta. This is how we got our boundary conditions for u at y equals 0 and u when y goes to infinity. So different color. These guys come from this definition. And we also have from before that v of x and y over u infinity is equal to 1 over u infinity times the quantity minus partial phi partial x, which is minus 1 over u infinity times the quantity of the square root of u infinity times nu times 1/2 over 1 over 2 square root of x f plus square root of u infinity nu times x f prime y over minus L squared times dl dx. Close the brackets. Which we can rewrite as 1 over 2 times the square root of the Reynolds number based on the distance x times quantity eta f prime minus f. And then probably everybody knows this, but just in case, what I mean by this is the following. So this Reynolds number is just u infinity times x over nu. So the length scale is just x. Okay. And then I guess let me draw a box here. So this boundary condition comes from here. Okay. Solutions to this equation are generally tabulated. So,
So it's just solved numerically?
yes. So the tables come from the numerical solutions. Or from someone who's very dedicated with a paper and pencil. Okay, so they look like this. This is what the table generally looks like. So you have a column for eta, a column for f, a column for f prime, and then a column for f double prime. Okay. Okay. Great. All right, so next, the next kind of related topic that we're going to talk about is skin friction. Which I don't know why that sounds like the name of a metal band. Doesn't it? Okay, anyway. This is the friction between a moving fluid and its bounded solid surface. All right, so if you remember, our shear stress is given as tau, and this is tau yx to be specific. And it's the viscosity times partial u partial y, which is in this case mu times u infinity f double prime of eta times 1 over the square root of nu times x over u infinity. All right, so I'm just going to algebraically massage this constant in front of the f double prime term. So we have rho times u infinity times the square root of nu u infinity over x times f double prime of eta. Okay, so this helps demonstrate the utility of having those tables for eta, f prime, f double prime. So you can, for any location eta, you can figure out what the shear stress would be. Okay. All right. And so it turns out that the skin friction coefficient which is called CF, is a dimensionless shear stress on the wall. All right, so CF is just tau yx at y equals 0 divided by 1/2 rho u infinity squared. And note that this quantity here is usually called tau subscript w for the shear stress at the wall. Okay? Okay, so considering that we want y equals 0, that means that eta is equal to 0. So we have rho times u infinity square root of nu u infinity over x times f double prime evaluated at eta equals 0 over 1/2 rho u infinity squared. And this we can look up in the Blassius table. So from the Blassius table, we know that this value is 0.332. Okay, and then we can also say, look it, we have a u infinity divided by u infinity squared, which is just 1 over u infinity. We have a density on the top and the bottom. And what we have left over is going to look like a Reynolds number. So we have CF is 2 times 0.332 over square root of u infinity x over nu, which is 2 times 0.332 over the square root of the Reynolds number. relative to the X location. All right, so this is the definition of our skin friction coefficient. And then this is valid for Reynolds numbers less than 10 to the 5, sometimes 10 to the 6. Okay. Okay. So if we go back to thinking about our plate, all right, so we have a completely flat plate like so, and then we have an incoming fluid like this. It turns out that when you have a geometry like this, the drag force experienced by this plate is purely due to that friction because of the fluid flowing over past it. Okay, if you have a non-flat body, so something that has heft in the y direction, then the drag felt by that body will be due to both the friction drag as well as pressure for like the normal component of the velocity on the body. For a flat plate, we only have friction drag. Okay, so for a flat plate, the drag force is entirely due to friction. And then let me say that bodies that have thickness in the y direction will also have a contribution to drag due to pressure.
So if you consider like a sheet of paper,
Yeah.
then in that case, wouldn't there be some lift?
We're only considering flow over the top.
Okay, so the pressure differential that's induced by the flow would not be considered.
Well, also angle of attack is 0, right?
Yeah, that's fair.
It's perfectly symmetric. So even if you had flow on top and bottom, this would not have lift just because it's of the symmetry. As soon as you angled it, though, you would both generate lift and generate a component of pressure to the drag force. Does that make sense?
Yeah, I guess in that case, I was just envisioning that the paper is not rigid, and then eventually, like it's gonna deform, and then there's gonna be lift.
So that's okay. So so that is different than this. We're imagining a rigid boundary, but even in the case of a piece of paper, from a theoretical standpoint, if the paper was perfectly flat, like in the mathematical sense, and the flow was perfectly parallel to the paper, you still would not generate lift. The only time you would generate lift is if there are, fluctuations in any of those things like real life would do.
Yeah, that's why I was just like having trouble thinking in a theoretical sense. That echo is destroying my brain cells.
Imagine how I feel when I have to edit it out after. Because the recording echoes too. It's very strange. Yes. And then I have to think about, do I want to impose my own voice with Lee's question, like the voice of God, over top of the video? The answer is no. But I can do
Was
like
it-
a
was
little black screen that's like, this was the question.
Like a
It was
little.
kind of a borderline dumb question anyway.
Wait, you have another question?
No.
Oh, no, it's fine. Okay, so if we wanted to write down the total drag, essentially what we're gonna do is we're gonna integrate that shear stress over the plate. So I'm gonna call my total drag D. No, I'm not. I hate that. I just told a student to not do that in 3,500. F subscript D. I'm like, why are you calling a force D? So hideous. I made him change
You
it.
naturally did.
No, these notes do it, so
Uh-huh.
now I know. Okay, so force of drag is equal to the integral of our shear stress at the wall times, and then let me put a coordinate system here. So this is y, of course, this is x, and then this is z. And I am going to integrate over this differential area. So this is dx, and then I'm going to call this dimension b. Okay, so we're going to integrate over b dx, and we're integrating from 0 to L, which is the extent of our plate. Does that make sense to everybody? So this dimension is L. All right. Okay, so I'm going to substitute in here my expression for tau W, which is just rho. Why is that being rewritten differently? So tau W is rho U infinity times the square root of times nu infinity over x times f double prime at eta equals 0, which we already know this is 0.32 from before. Right? Okay, so a lot of this stuff is constant with respect to x, so I'm gonna pull it out front of the integral. So I have force of drag is b times rho times u infinity times the square root of nu times u infinity times 0.332. And now I'm going to integrate from 0 to L x to the minus 1/2 dx. What do we get? No one? And I'm going to write u infinity as u infinity to the 3/2 now. Nu to the 1/2, 0.332. No one? Come on. Don't make me.
Answer, but the echo is destroying me.
You could have done it in fewer words than that.
Could it have though?
Yes.
1/2. I don't know.
It was close. It was close.
Seem real pick and choose here.
Okay, so I have Oh, you guys didn't even help me. It's a 2.
Okay.
I was like, wait a second. Okay. Thank you. 1/2. Or sorry, the 2, so this is 0.664 now. And then I have square root of u infinity times nu times x. Oh, sorry, times L, because I evaluated that integral. Make sure I didn't forget anything here. Okay, so we find that the force of drag scales with u infinity to the 3/2 and as length to the 1/2, right? And
Isn't
we
there
can
something related to the Mach number?
what?
Isn't that like the speed of sound?
The speed of
Related to
sound is
the-
related to the Mach number, yes.
Well, I know, but like the square root of u infinity nu.
So there's no, c is the speed of sound. It's not in here.
Never mind. I was just associating. Never mind.
Okay. Okay.
I got like 0 C plus.
Clearly.
Yeah.
Jalen.
Sorry.
Okay. Okay. One last thing that I'm going to write here is we can also write the coefficient of drag then for our flat plate as the force of drag divided by 1/2 rho u infinity squared times a, which is, we have our 0.664 times b times u infinity square root of rho u infinity L. I did a thing with, oh wait, and I forgot, hang on. I forgot a mu in here. Rho mu u infinity L. So I took the nu and turned it into mu over rho, and then okay. Okay, great. And then divided by 1/2 rho u infinity squared times a, where a is just b times L, right? So now I can cancel some things. So I have that. I have this. I have, that's all. Okay, so then it turns out that this is now, we get our 0.332 back because we have 0.664 divided by 2. And then what's left over is a square root of the Reynolds number based on the length of the plate. Wait, you're right. Oh, yes, you're right. I can't read, and this is actually 1.328. But 0.332 just felt good to me in the moment. I don't know.
All right.
It just felt good. Yeah. Like, let's go back to that. I like that 0.332 number. Anyway. Yeah, so this is our coefficient of drag. Nice. Cool. That's all.